C'est bien, l'appel Wikispace. C'est notre expert spatial. Il a baigné dedans.
He's our space expert.
Il est maquettiste.
He's been deep in this forever. He makes models. One of his models is on exhibition at the Baikonur Cosmodrome. So he's a real expert. He's got the golden book of Cité de l'Espace. And he might intervene sometimes and send us a few friendly words. So Serge will come and bug us a little bit. But you will love speaking to him, and he will be delighted to exchange some views with you. So spasiba, as they say. I don't know the status video-wise. Well, we are starting, so Lionel, the stage is yours. Good afternoon, everyone. For those of you who don't know me, I'm Lionel Suchet. I'm the Deputy General Manager of CNES. It's a great honor for me and a great pleasure too to be in front of you today to host this afternoon's session for many reasons. CNES, the National Center for Space Studies, has been involved in manned flights for a long time. In 1966, General de Gaulle was the first man from the West to visit Baikonur, which was quite secret. And in 1982, 35 years ago, Jean-Luc Chrétien was the first European to fly. I don't know if Jean-Louis is with us, but happy birthday. Since then, we never stopped weaving collaboration relating to manned flights with our Russian, American friends, the Chinese, of course, and a major part being played by ESA. I have been involved, many of you know it, for 30 years now with CNES on the manned flight subject. I'm deeply moved to be in front of you today. I have many friends in the attendance. For this theme session, we have prepared two round tables. They will be related to the Congress motto, "Space is my future." There are many reasons for which space is and will be our future. We could have looked at it on an economical point of view. Space is getting more and more into our daily life. Space data are meeting new challenges, society challenges. We could have discussed space involvement and space applications, but we chose two specific topics which are fundamental for our future. Space as an exploration target, and space as a tool to help protect our planet, and God knows that is important today. So before we start these two roundtables, we have a guest star to launch this. Before we go any further, going higher, seeing the Earth from another point of view calls for technological performance, but also calls for a lot of dreaming and thinking, and it's shared between the air industry and the space industry. And here, when I say air, space, dreaming, you think of Night Flight, which is Vol de Nuit. It's another book from Antoine de Saint-Exupéry, It's a rather extraordinary book about what he was thinking about during his long flight overnight. Saint-Exupéry used to take off a few hundred meters from here. He departed from Toulouse to go on his legendary flights. There is no doubt that Saint-Exupéry would have had a place with us today. But our guest star is related to a much more recent event, the 26th of July 2016, little more than 1 year ago. An extraordinary aircraft lands in Abu Dhabi after an extraordinary round-the-world trip. Extraordinary because the trip was flown without fuel. This aircraft is powered by the sun. It's solar impulse. It's more than a plane. It's a team, a passion, human adventure that will have a big impact on the story of aviation and probably humankind as well. Please welcome a doctor and explorer, the man at the origin of Solar Explorer, Mr. Bertrand Piccard. And before Bertrand gets to the stage, we are going to show you a quick film on the Solar Impulse adventure.
Achieving the first solar flight around the world. This is the story of two men. Bertrand Piccard, psychiatrist and explorer, and André Borschberg, engineer and entrepreneur. A team driven by a vision of the future and a passion for innovation. And the first airplane of perpetual endurance, able to fly day and night without fuel. Together with their partners, they wanted to show the power of pioneering spirit and clean technologies to bring solutions for a better world. Solar Impulse, the adventure showing that change is possible.
It's a bit the moment of truth, because you simulate, you calculate, you imagine, but there is nothing like testing and doing it in real. We deeply believe that we can achieve impossible and incredible things with renewable energies, like flying around the world with no fuel. And if this works, of course, everybody can do it on the ground to make a cleaner world. And this can be your way to be with us in the plane.
And this was a scene in Abu Dhabi early this Monday.
Dans ce journal également,
on its way to the moon. In fact, it is now ultralight plane is powered only by the sun's rays.
Between March and July 2015, Bertrand Piccard and André Borschberg flew without a drop of fuel from Abu Dhabi to Oman, across the Arabian Sea to India, Myanmar, China, Japan, and over the Pacific to Hawaii.
How are you feeling after all that time? You broke a world record in terms of solo flight, a few hours.
Resuming the round-the-world adventure in April 2016, Solar Impulse continued from Hawaii to California and New York, across the Atlantic to Spain, then Egypt, and made it back successfully to Abu Dhabi in July. Today the challenge is no longer to conquer the moon. The challenge is to conquer quality of life on Earth. Our world desperately needs the implementation of clean technologies to reduce the energy consumption and the waste of natural resources.
Hotel India Bravo, turning final, 02 right.
This airplane was not built to carry passengers, but to carry a message. The world could reduce half of its CO2 emissions by replacing old polluting devices with new clean technologies, like those used on solar impulse.
I am inspired by your pioneering spirit.
You know, Mr. Secretary General, if an airplane like Solar Impulse can fly day and night without fuel, the world, of course, can be much cleaner.
Inspiring generations, promoting innovative solutions to the challenges of humanity, inventing a brighter future. Solar energy made it possible to fly many days and nights in a row without fuel, crossing 2 oceans and remaining airborne longer than any jet plane in history. 2016 has seen the completion of this pioneering adventure, flying 40,000 kilometers round the world without a single drop of fuel.
More than an achievement in the history of aviation, Solar Impulse has made an achievement in the history of energy. Let's take it further!
Like Solar Impulse, the clean tech revolution has taken off, presenting new ways of thinking and doing to achieve the impossible. And you can be a part of it.
Good afternoon to everyone. I'm muted. Yes. Good afternoon to everyone. You know, you might wonder what is the reason why a solar airplane pilot comes here for an astronaut meeting. And actually, it all started with the early astronauts of NASA during the American space program. Can you please put the pictures on the screen like I asked you? Thank you. When I was between 10 and 12, I had the chance to live in the United States, very close to Cape Kennedy. My father made a submarine for Grumman Aerospace. He drifted in the Gulf Stream for an exploration mission, and in collaboration with NASA and US Navy. So I was all the time in Cape Kennedy, watching 6 Apollo take off. Here, this is Apollo 9 taking off, together with Bill Anders and some CEOs of NASA. And I was so inspired by this conquest of space, so inspired by these people who wanted to achieve the impossible and gave themselves the means to do it. It was not only the dream, it was the commitment and the perseverance to fulfill the dream. And I remember very well, at the takeoff of Apollo 11, I thought I would like to have that type of life. Well, I was 11. And by the time I could start to explore, the moon program was finished. But I always had a compass in my head, or maybe my heart, who was not showing the north, it was showing the unknown. It was showing what had not yet been done, mainly what was still considered to be impossible, exactly like the heroes of my childhood. So this is why I tried to do things that were considered to be impossible, like flying around the world non-stop in a balloon. Well, that was a slow orbit, I have to admit. It was non-stop, it was a real orbit, so when I heard the definition of people who could be member of the Space Explorers Association, I can qualify. It's 1 orbit, 20 days, not very fast. And but it was not a clean flight. I was pushed by the wind, but we needed to have propane to heat the envelope of the balloon. And every day I was afraid to fall short of gas. And at the landing, from the 3.7 tons of liquid propane I had at the start with my friend Brian Jones, there was 40 kilos left. 40 kilos. So it's clear that if we wanted to fly longer, we had to change the paradigm. The limiting factor was fuel. So if we wanted to fly forever, without refueling, we needed to get rid of the fuel completely. Crazy dream. I have to admit that I didn't dare to speak about it to a lot of people until a capsule of my balloon was brought to the Smithsonian Air and Space Museum together with the milestones of the heroes of my childhood. And then I had the impression that for me it was a complete cycle that was closed, but maybe also in a way for aviation. From the first airplane to the moon, going through commercial airplanes, flying with 500 people across ocean, breaking the speed of sound, everything had been done. People in space, everywhere. So maybe we could start a new cycle of aviation with no fuel, completely clean, having a solar-powered airplane that would be able to capture the energy of the sun, store it in batteries during the flight in order to spend the night and make as many cycles as we wanted. But when I brought this vision to the aviation world, they all told me it was impossible. And why that? Because the plane had to be 72-meter wingspan, 234 feet in wingspan, but with the weight of a family car. And the power available was the power of a scooter. So of course, nobody thought it could be done. The structure of the plane in carbon fiber itself had to be 10 times lighter proportionally to the size than the best competition glider. 10 times lighter, not 10% lighter. So of course, we imagine how many people thought it was impossible, and we had to find people who did not know it was impossible. And who was that? A shipyard. The shipyard who had built the hulls of the Alinghi boats that won the America's Cup twice for Switzerland. So if you have a country like Switzerland who has no access to the sea, winning the America's Cup twice, it means the shipyard must really be good. And they built the plane light enough. And for us, it was a huge lesson. It meant that we were building a plane with people who had never built a plane. And this shows how much in our world we are taught to think only in one direction. We are taught to think in what we have learned. We are prisoners of our habits. We are prisoners of our beliefs, prisoners of our paradigms, which means that it's very difficult to imagine the future in another way that we have experienced the past. So it's clear that it's very dangerous if we want to speak about the future to think in a straight line. That we ignore what is left and right, when we ignore the question marks and the doubts, when we think we can just go straight until we find an obstacle and then we are lost. If we want to be explorers, we need to think in every direction. Of course, we don't know at the beginning which is the way to think that will lead us where we want. And this is why we need this spirit of trying, explore, pioneering spirit. We have to accept the risk of failing. We have to accept the risk of losing control. And then we will find the way that will bring us to success. In another word, I think we have to understand that life potentially can be a firework in 3 dimensions. For every point, there are a lot of lines going everywhere. And this is the way we should think. Explore the vertical axis, explore all the ways to think, all the ways to behave, all the ways to understand life, all the ways to understand the world, and take the one that leads us where we want to go. A little bit like in a balloon. You need to drop ballast in order to climb, to change altitude. And when you change altitude, you go through all the different metallurgical layers and you monitor the atmosphere. You know for each altitude which direction you have. And then you get a 3-dimensional vision of the future. And you stabilize your balloon at the altitude where the wind goes where you wish. And like this, you are free. You are free to think in every direction. You are free to invent. You are free to create. And you are free to get rid of everything that keeps us prisoner from the past. So Solar Impulse was not just a solar-powered airplane. It was the first airplane of perpetual endurance. Theoretically, there was no weather problem if we did not need to rest as a pilot. This plane could fly forever. So imagine what it means. You are in the middle of an ocean. The plane flies slowly, so you take several days and several nights to cross the ocean. You look at the sun. You look at your 4 electrical motors with big propellers turning. And you have no noise. You have no pollution, you have no fuel, and you can fly as long as you want. And suddenly you think, wow, I'm in the future. I'm in a film of science fiction. And actually, not at all. Not at all. You're only in the present. You are in what the technologies of today allow to do today. And it's the rest of the world that is in the past. It's the rest of the world that is in the past with old systems, old devices, combustion engines, badly insulated houses, old systems for lighting, for cooling, for heating, a grid of electricity that is completely outdated and inefficient, old industrial process. And this could be changed quite easily because the solutions exist today already to divide by 2 the energy consumption of the world, divide by 2 the CO2 emissions. And this could be profitable. It could create jobs. It's an industrial market. So each time we had to land, it was like going back in the past. And it's clear that at the end of this flight around the world, landing back in Abu Dhabi, there was the crucial importance of explaining why we had done that. So the most important picture is not the plane, it's not the pilot, it's even not the team, even if it was so crucial to have such a great team. No, it was the banner that we put in the front. Take it further. Take it further. We've done the first step, exactly like the first satellite was the first step, the first man in space, the first man on the moon, maybe once the first man on Mars. It's only a first step. The rest of the world has to take it further. The rest of the world has now to implement the solutions that exist to make a better world. And so much has been explored in the last century, but not quality of life. We need so much more about fighting poverty, about education, about governance, human rights, protection of the environment. And here we need the same commitment that what there was for the conquest of space. But it has to be done also by the political leaders of this world. This is why when I was this morning on stage, I had 2 minutes to explain, maybe I can say it now in a few more words. It's the responsibility of all the people who are famous, all the people who are holding microphones in front of the media, all the people who are talking to heads of states, to tell the truth of what exists today. We are in a crucial moment for survival on the planet. The situation is much worse than what most of the people believe in terms of pollution, in terms of depletion of natural resources, and in terms of climate change. But only speaking of problems is useless because we depress everybody. We need to speak of the solutions. And today the solutions exist. And this is what I am committed to do right now. I've created, with the Solar Impulse Foundation, the World Alliance for Efficient Solutions. It's a world alliance to bring together startups, corporations, institutions, universities, who have found an existing product, process, program, or clean technology in order to be able to protect the environment in a profitable way. It needs to be profitable, otherwise it's completely a dream. The Greens have shown the dream of protecting the environment in the last years by threatening consumption, comfort, growth, mobility, and it does not work. We have to show that today, if we would replace all the old infrastructure and devices by the new modern ones, it would create millions of jobs, make a lot of profit, and have a clean growth that would replace the dirty status quo of today. And I've committed the Solar Impulse Foundation to bring in 2019 1,000 profitable solutions to the government, 1,000, and to tell them this is what you can base your energy and environmental policy on, not on at minima negotiations, but on the reality of existing technologies. So we see that whatever we do, we go on space, we go in protection of the environment, we go in politics, whatever, we need this spirit of exploration. Like what I want to show here on this picture, this is actually the last picture I did during the flight around the world in a balloon. It's a window, porthole of the capsule of the balloon. It is frozen by the moisture of the night. And on the other side, you have a rising sun. But you will never see the rising sun if you don't first go through the ice. And this is what so many people are afraid to do. Because in life, we have ice. We have problems, we have doubts, we have crises. But so often the people prefer to suffer in the problems they know, rather than to take the risk of going through the ice to see what there is on the other side. So whoever we are, whatever we do, astronauts, scientists, or whatever, father, mother, children, teacher, every moment of our life where we have some ice, where we have some problems, where we don't see the future in a clear way, we have to understand that the adventure starts at that moment. This is where we have to be creative. This is where we have to be explorers. This is where we have to drop everything that prevents us to move into a more creative way of seeing the world. In other way, an adventure is a crisis that we accept. And a crisis is an adventure that we refuse. And this is a decision we can make for our life. We cannot all decide to be astronauts. We cannot all decide to go on the moon. But we can all decide to be explorers. To take these moments in life and understand that confidence, trust, is more important than courage. Because in courage, you need to fight a lot. You need to fight even against your fears. In confidence, in trust, no, you don't need to fight. You just need to put yourself in a new situation and observe that humankind have this fantastic capacity of having access to their inner resources each time they need it. Of course, each time we live in our routine, in our certainties, we'll never find this potential. But each time we get into the adventure, when we lost our zone of comfort, then we will discover what human beings can really do, how much resources, skills, potential, capabilities we all have inside of ourselves. And this is what I wish that we all discover, that we all explore, because it's really worth it. Good luck to all. Plaisir.
Merci beaucoup, Bertrand.
Thank you very much, Bertrand. He is at the very heart of our topic, exploring to make our world a better place, to fight with courage against the cleavages of our technological fields of activity where we don't fight together. And that's where wealth comes from. And that's the basis of the theory of innovation, as Bertrand explained to us. And, by the way, for the gentlemen of the space industry, we have to be very careful because we've learned how to have lighter vessels. And so for space stations or space exploration, you have to go and see boat manufacturers, as you've seen. So exploration, and we'll see Bertrand will come back on stage to chat and ask questions with the different speakers. So how will the roundtable work? The first roundtable is about exploration. For always, exploration and space has been seen by mankind as an infinite field of observation to begin with, and then exploration. It's also an inexhaustible source of inspiration for future generations. And today it remains, and since the beginning, has been at the heart of space agencies. Therefore, exploration of space is something that's very important for all of us. So we're going to be talking about this in the roundtable. I'm going to call up one by one 3 speakers. We will be moving away from the Earth, if you don't mind. We'll start talking about low orbit, and then the Moon, and then Mars, and beyond of our solar system. The speakers will remain on stage once they've made their 10-minute presentation, and then we will talk together about this topic. So to talk about exploration, the first person which I would like to call on stage is Thomas Pesquet, astronaut from the ASC, the 10th French astronaut to come back to Earth after the Proxima mission. Thomas Pesquet.
Bonjour à tous. Alors moi, je vais peut-être commencer par dire que je suis très honoré d'être ici. Bertrand a fait l'orbite la plus lente.
Bertrand flew the slowest orbit, and I flew the most recent one, the one that ended in June, with me landing back on Earth. I'm the new guy in the Space Explorers Club, meeting peers that I used to admire when I was young. So it's a great honor to be here. And it's not an easy job they've given me today, because during this afternoon's program, we're taking you all into space. So I'll take you on a low orbit, which is not bad in itself, but I'll take you to the Moon afterwards. And that's not an easy job. So here the first slide is the chronology and the geographical map as well. We'll discuss low orbits. I'll tell you what we're doing today in the ISS. This is space exploration today. Then I'll tell you what could bring us to the Moon. I'll try to give you a short history of the past 10, 20 or 30 years to see what drives the space exploration we're doing, and see how we can carry this to the future and what we can expect in a very near future. Then I will give the microphone to Sylvestre. He will take you to Mars, which is not that easy either. And then we'll finish with the exoplanets. Low terrestrial orbit. You have seen photographs looking very much like this one. This is what happens in the space station. Lots of cables, scientific experiments. And the space station, lots of people in the room flew to the space station well before I did. It is a research station, it's a lab. We use the zero gravity to explore things we cannot explore on Earth. So we are driving science forward. We try to bring progress, scientific results that we cannot get on Earth. But it's not only that. That wouldn't be a goal in itself. We do exploration. And people say, how do you do exploration? You stay around the Earth and you go nowhere. Geographically, yes, we go around the Earth, but we prepare the future explorations. I had the pleasure to fly with Peggy Whitson The experiments we did was about the astronauts' health, the loss of vision. Some astronauts will have their eyesight changing in space. We can't explain it, but we would very much like to. If we go for a long time in space, we have to stay operational. So man in space is necessary if we want to go further, and it is at stake now, and what we are doing in the space station is about this. Technology, what makes it possible for us to work in space, and we're also trying to improve that, to go to the moon, to Mars. Robonaut is robotics technology. During my mission, we made some experiments on controlling a rover remotely, and we are going to need that for our remote operation of machines, because clearly the next step will be international cooperation, of course, but collaboration between man and machine too. This photograph here with Peggy Whitson, I don't want just to show you my nice ESA suit. I want to show you BEAM. It's a module that is attached to the space station. It's inflatable, and it's a good demonstration of the new technologies we are testing on board the ISS, and this will help us to go further to Mars, to the moon, and we will use this during the trip. So, a few words about what we are doing on board the space agency. We look towards the Earth, of course, but we're also looking to the cosmos. This photograph was taken from the space station. This is a good view of the moon, and I'll tell you why we think we can get there in a few years. You know, space world, it's easy, we create the future. But if you want to create the future, you have to look back to what we've done in the past. So we'll look back for the past 60 years during the exploration of the moon. What happened? What were the motivations, the drivers that took us to the moon, and will take us back there in the coming years. In every sector, you've got a golden age. Golden age for moon exploration was a trip, 14 missions in 2 years. This was the driver for the space race. It took us to the moon, and it was driven by technology. What we needed was to develop the technology that would take us to the moon and bring humans to the moon. There were many failures, but this is the price to pay. When the road is difficult, Bertrand said it, it's not always as planned. But we had some incredible successes. Luna 2 reaching the surface, and then a photograph of the hidden face of the moon. And this is what you see bottom right. In the 60s and 70s, we capitalized on these first steps and accelerated the number of missions. It was incredible in the 60s and 70s. You know the context. It was the moon race between the US and Russia. There was a real political will, but lots of science. We didn't just go there to plant a flag. You have some photographs of Apollo 17, the first steps of a man on the moon, the Apollo reflectors, and the great success was, like Luna 16, the automatic retrieval of samples. And you thought everything was fine, but suddenly it stopped. In the 80s, no mission went to the moon because the race was won, and it wasn't interesting for anyone except one category of people, the scientists. You know, as I know, that when a scientist has something in mind, he doesn't let go easily. And in the 80s, we proceeded to a detailed analysis of the samples brought back by Apollo and Luna. So we determined the most likely hypothesis, which was that the moon is a part of the Earth that got freed by an impact. In the 90s and in the 2000s. There was restart of the lunar missions. We're not going there for a race anymore. We're going there for science. And science is the driver. We want to go to the poles. We want to study our satellite in details. It's technology-driven, but not that much. We bring 150 kilos. We've got to get there fast. It can't be too expensive. And this is how the missions succeed. Politics are playing an important part too. We've got some new players like Japan, Europe, India, China. And this lunar exploration, which was bipolar. We found water with Lunar Prospector, and we've got high-res images with Talero and Selem. In the 2010 years, everything changed again. We still had lunar missions, but if you look at the breakdown, USA 3, China 4, and the others don't have missions anymore. So we are back to a rather bipolar job, and it's a race between China and the US now. The main focus is science again, and we see that this competition between China and the United States is probably the driver that will accelerate our speed to the moon. So looking into the past is great, but what does it tell us? It tells us that in the next 10 years, we'll have lots of opportunities. Drivers are science. Science is always probably the main driver for the moon. We would like to go back to the impact crater on the South Pole. We would like to find the moon mantle, and it would be of the utmost value. Politics is still here. It's the US against China. But what part can the others play? Us Europeans, CNES, and the other agencies, can we imagine some major missions in collaborations to go to the moon? We discussed technology. We have the parts of the puzzle to go back to the moon. We have a vehicle. It's Orion. It's ready. It could take astronauts to a low orbit around the moon. We have landers. We have rovers. We have to put all this together and go back to the moon. Lunar exploration. Astronauts are ready. You will always have some volunteers for this sort of adventure. Bertrand said it's an adventure. But at the end of the day, the missing driver in all that is probably the one I put in the middle of my presentation there. It's economics. Protecting the environment is fine, but it has to be profitable, and it has to be compatible with the economy. We are opening to private operators now. Remember the Google Lunar Prize? It's been postponed 1 year, but it's still real. And it goes together with the scientific exploration. We've got a new profitability that didn't exist and will be the driver for the 2020s. I didn't invent anything there, and I am not the one who will design a lunar mission, but agencies are always one step ahead of everyone. They've already considered that. It's an artist's view of the Deep Space Gateway. It gathers NASA, ESA, Roscosmos, probably a few others, we hope. This is a station orbiting around the moon. It will be shuttled by Orion, and this is today's concept of a great international lunar program. It could be, it's risky to give a date, but it probably would be around the 2025 or some. With this, we can do remote operation, send landers to the moon, some astronauts could go there and back, and with this, we could probably validate the technologies to go to Mars. Mars is like crossing the ocean with a plane. You don't do it before you tested technologies, and the Deep Space Gateway would be the best possible way to be sure of our technologies. and one day go to Mars. So the second phase of this project, you know it, it's very dear to the ESA director, is the Moon Village. And this consists in settling on the moon surface. We have some very advanced studies at ESA. We could build some dwellings and probably settle in an international village, gathering commercial and political interests on the moon. It's probably utopia, but it's probably what we need if we want to make progress in space exploration. This is what I wanted to tell you. We started from the ground, went to the space station. Now we're on the moon surface, and I will give the stage now to Sylvestre, and Sylvestre will take us to Mars.
Tu restes avec nous?
Thank you, Thomas. You're staying with us.
Maurice est astrophysicien. Il travaille à
l'IRAP. He's an astrophysician working at IRAP.
En planétologie.
It's planetology and astrophysics studies here in Toulouse. Sylvestre is involved in many planetology missions.
Un instrument assez extraordinaire qui s'appelle ChemCam, qui est
He's
sur Curiosity.
Of an instrument which is presently on Mars, and he's preparing the next SuperCam that will be on the Mars 2020 mission. So let's go to Mars. Thank you for this great introduction. I'm most honored to tell you about this Mars business, and from my introduction I can tell you the machines are here to prepare the arrival of man on Mars, and I hope you will follow me in this direction. We'll discuss exploration. If you counted what you saw on Thomas's table, there's roughly 100 missions to the moon. For Venus, we're around 43. We are at over 48 for Mars. For the giant planets and their satellites, we're beyond 10 missions there. We are everywhere in the solar system. We have just had 60 great years, and it goes on. So I'll focus on one of these planets, Mars. Initially, it was ordinary, if I can say. Small planet, far from the sun, rather cold. And you will see that it has an incredible destiny. And I will start by showing you this great view from Curiosity sent us that. It's a NASA rover on the surface of Mars. This is a dune field climbing to the sharp mount. It's a beautiful scenery, but be honest, the atmosphere is extremely thin. It's cold, no liquid water, no geological activity. It's a planet, even though I contemplate it with pleasure every day, but it's not really heaven. But if I look at the past, I see traces of another Mars. Bottom left, you can see traces of a river running for 300-400 kilometers. It's a catastrophic flow, as we say. There is a delta too. And on the right, it's a bit harder to understand. It's the result of Mars Express, confirmed by an American probe. It's an alteration. These are minerals that are here only because water, liquid water, has been there for a long time. And here we can date Mars around 3.5 billion years. It had liquid water, rather intense geological activity, and this was possible thanks to a rather thick atmosphere, dense. It was thrilling, and it would ask two questions. In these days, was it habitable? And if it was habitable, did life manage to develop there? This is the big interrogation on the Mars program. We have three directions there. First is life. That's the main question. Was there life on Mars? Do Martians exist? Habitability, traces of life, the carbon cycles, prebiotics, chemistry. And to support these studies, we need the two major characteristics of a celestial object. Geology, climate yesterday was probably very different to what it is today. It could probably depend on the planet's inclination. And my successor, François Forget, telling you about exoplanets, he is the world specialist for Mars climate, so I won't tell you any more on this. Sorry for that. So,
geology
is also a major pillar. If you want to understand how a planet develops, its structure, its crust, and we know just about nothing on the inside of Mars, and this is why NASA is sending the InSight mission in 2018 to Mars, and in France we built the seismometer in collaboration with other European countries to try and understand what's inside the planet. So the Mars science will lead to a Mars program. The Mars program will follow the changes of all other programs, as we've noted on the Moon and probably on the other planets. It will start by failures, and Thomas said it. Bertrand said it before Thomas. Failure is possible. On Mars, we had statistics. We had about 50% of our missions that failed. It's better now. It has improved. But you have to accept failed missions. You also have to accept some of them succeed. And sometimes you have flybys, a mission just going near the planet, like we've done on Neptune and Uranus, the giant planets. We've done it on Jupiter too. And of course, then we want to go into orbit, and we have to slow the vehicle down, and the Graal is when you land, you make a lander, like a Viking or a Phoenix, or bases like Spirit Opportunities. These were measurement stations like Pathfinders, and the cream on the pie would be the rover, like Pathfinder, Spirit, Opportunity, Curiosity now. So you see that complexity increases. What is the next step after all that? It's for scientists to get some samples flown back. This is the ultimate limit. And today we have nothing. We never brought samples back from Mars. A vehicle would have to take off, orbit, send a vehicle, bring this back. Robotics probably would work, and I think we are ready to send people on Mars now. We're not very far off. And around all these ideas, we imagine a Mars program. We live a great time. We have 6 orbiters today around Mars, 3 from NASA, 2 from ESA, and 1 from India. And on the surface, we have 2 rovers. Spirit has stopped, but its twin is going on. It's Opportunity. We have Curiosity too. We've got 8 vehicles that have to be piloted every day. The future in 2020 looks great. We'll have 3 vehicles on the surface, Europe, China, US, and then other missions orbiting India, United Arab Emirates, an orbiter from China. It all accelerates, and then we will go for samples. It's very difficult to summarize all the discoveries this program brought us. I'll focus on the one I know better. This is a very good selfie from Curiosity. You cannot see the arm, it's logical. The arm took the photographs, and you see that the rover is starting to age. There are some damage in the wheels. It's metal, it's fine. You see some dust on the surface. And on the left, the arm could drill. And after 2 years, we have made discoveries of liquid water, energy, carbon, nitrogen, phosphorus, sulfur, water with a neutral pH. And the conclusion is that Mars in the past was habitable. It was an idea, we discussed it, this is why we sent Curiosity, and it's a major discovery, because now, if I look at the statistics, we have 2 inhabitable planets, the Earth and Mars. Were born 54 billion years ago. Mars is hot. It had liquid water very early, then it lost its atmosphere. We're starting to understand the reasons for this now, and it's set in its past. So when I look at Mars, I look at 3-4 billion years ago. On the opposite, the Earth continued. But initially it was like Mars, and then life settled, took 3 billion years to settle, and became more and more complex, then exploded in the last 500 million years. But it's a very young planet now, from what we can see. Due to erosion from the wind, from water, plate tectonics, the Earth has no memory. So everything we learn from Mars will be useful to understand the Earth, to understand how it became inhabitable. But unfortunately, the Earth lost its memory. Mars is more than Mars then. It's trying to understand Mars. And the question of how to live in the whole of the galaxy. But don't think it's only Mars and the Earth. 2 planets is quite a lot. But it's not a statistics, but when you look at the universe with all these exoplanets, with 2 out of 8, there's probably a few billion that are inhabitable, and we have other options in the solar system. I'll tell you about our 4 best options. It's the ocean world. You've got Encelad and Titan around Saturn, observed by the Cassini mission. Encelad with its geysers, hinting for a sub-ice ocean, and Titan with the methane lakes. On the right, 2 Jupiter worlds, Europa and Ganymede, with sub-ice oceans in contact with the rock. This is the ideal configuration to find an inhabitable world. Missions are on the way. The JUICE European mission from ESA and the NASA mission Europa Clipper. So I've reached the end of my time. This inhabitable, you've got to go further, so we'll go and look for traces of life. This is the NASA rover for 2020. This will take over from Curiosity, same size. It will be probably 150 kilos heavier, because we've got a sampling mechanism. We can sample things, put them in small bottles, and then the samples will be dropped along the way with a mission for the space agencies to bring them back one day. But if you look, there are some very nice things on this rover. You see helicopter, it's what we call Heli-Scout. It's a drone on which the GPL is working now. It's extremely complicated, but they are fighting to have this explorer that could go out and take pictures to prepare the way, because with an altitude of 2 meters, it's difficult to find your way, and the little drone can take photos to map the way. And there's a small experiment called MOPSI. You can see it here. MOPSI is an oxygen production unit. Why make oxygen? Well, it's for you we're making oxygen. It won't be enough for the time being. You should take deep breaths, but not too often. But we'll produce 97% pure oxygen from CO2. If you heat it over 600 centigrade, you have a catalyst effect. a chemist called Paul Sabatier invented that. We're quite proud because this is the name of our university in Toulouse. So we're producing oxygen. And if you think about it, all the robotics missions have this little preparation aspect. Curiosity was to measure the radiations. This is one of you on the surface of Mars. It's an artist's view. I used that to show you the scale of these dunes. It's the Rebus, it's the Charton Mount entry point. And for me, there's no question. It's obvious a man will go on Mars. The question is when. I cannot answer any questions on that, but I do know, I'm certain, that the first man who will walk again on the moon is born. How will we get there? It's not very clear yet. Shall we use the moon as a first step? Will it be an orbit? The trip is complicated because of the radiations. And what strategy? Are we competing one against the other? It could be a good driver for the moon. It worked. And quite often cooperation makes it possible to gather all the extraordinary means we need. So we are there. We are expecting. We have the machines and we're just waiting for man now. Thank you.
Merci beaucoup, Sylvestre. Alors,
thank you very much, Sylvestre. So, ever further, ever higher. As we said earlier on, François Forget is a research director in the CNRS, the National Centre for Scientific Research in France. He's a world specialist in planet atmospheres, and he's going to be talking today about exoplanets. He works in the Dynamic Meteorological Service. Exoplanets.
Bonsoir à tous.
Good evening, everybody. I'm going to continue in French, therefore, because can you see my slides?
Voilà, c'est arrivé.
It's a very big honor for me to be here. I know that many of you, I've been following many of you with passion for a long time. We're going to go beyond Mars. We've spoken a bit about different aspects. We could go through Pluton that I worked a lot on in the New Horizons mission, and we're going to go towards the extrasolar planets. You no doubt know for a very long time it was very difficult to look at extrasolar planets, to detect them and to observe them, because just besides a star, the contrast, they're so blinding, these stars, that you can't see much. And 20 or so years ago, thanks to astrophysics tricks based on the fact that you can detect, even if you can't see it, you can detect the planet, you can detect the movement induced by the forces of gravity on the stars and the Dopplers, and message the planets. When you can see it from the side, you can see the shadow of the planet. And there are many other methods that were also used to discover up until 3,000 planetary systems so far. And when we look at the stats of all of these measurements, here you can see the mass or the size sometimes of the planets that we have detected according to the date of discovery, and you can see that we're discovering more and more of them. And little by little, we're able to detect planets of the size of Earth and to take an interest into these rocky planets, which really fascinate us. So this activity is ongoing because not only are we detecting them, but we can characterize their orbits, we can characterize their mass or their radius, and we can continue on Earth already, thanks to very ambitious projects of telescopes and in particular spectrometers to measure and detect these planets by velocimetry. And in space, there are 3 missions that are almost ready, sometimes anything that consist in continuing drawing up this inventory, and where we can detect the shadow of the planet. You have the Swiss ESA satellite, Cheops, which will be going out in a few months. A NASA project, which is quite ambitious, which is going to also observe a large number of stars that are brighter than the ones that could be measured by spatial telescopes previously, the CORO, the CANES, and the Kepler satellites of the NASA that detected millions of planets. And so TESS will be able to identify brighter stars, so it's very complementary. Meanwhile, in some 10 or so years ago, there was a very ambitious program by the European Space Agency to do a very big list of planets. So what have we discovered in these thousands of planets that we've discovered? I'm going to go very fast, of course. The first lesson is that there is an incredible diversity, which really surprised us. It surprised all astrophysicians. We find new types of planets, super Earths, mini Neptunes, hot Jupiters, ocean planets, some very strange things. We find planets around all types of stars, including multiple systems, very strange orbits, sometimes very eccentric, which we don't see in the solar system at all. Very compact systems with lots of planets within the orbit. You can see the planetary migrations. We can see that a large number of planets are starless, and they're in the interstellar space, wandering around. And above all, and this is a scientific discovery, we don't have time to go into the details, but the big lesson is very simple, it's very basic, is that we have proven, it's recent, it's statistic, that most stars are surrounded by exoplanets of small size, so rocky planets. And this is something that the general public was waiting for, even you. In Star Wars, in Star Trek, there are planets everywhere. We didn't know. We demonstrated this, and it's a very important piece of news. And of course, when we say this, we want to know among all of these planets, and we know that there are lots of other Earths in terms of size, which are suitable for life. Can we detect life there? And in this context, of course, this raises a lot of problems. What is life? What do we need for life? So we're going to simplify things, and we know what we're doing in our environments. Generally speaking, life as we know it, and even life as we might imagine it, above all needs one ingredient, it's liquid water. And for the life to be detectable, there needs to be liquid water at the surface. So that restrains the scope of possibles, and for example, the worlds that we will observe must not be too near their star, otherwise all of the water will be in vapor form, not too far away, otherwise it will be ice. Therefore, we have a notion of inhabitable zone, but that is not enough, otherwise the moon would be inhabitable. It's not the case. So in addition, we need an atmosphere. We need the right atmosphere. And here we're facing the unknown. We have too few examples in the solar system, and when we take an interest in inhabitability to know whether the Earth is exceptional or not, we have a problem, and that's that it's too complicated to imagine the other atmospheres. What's happening on Earth? Can we find the same thing elsewhere or not? So the next step is to observe the environments and atmospheres in the exoplanets, and that's where I come into play. That's the heart of my profession. And so there are methods that you can apply on the big hot planets that we've already discovered, and we can, when we're lucky enough to see a layer system, we can do transit spectroscopy, so we can measure the electrons that go through, or a difference by contrast. We can understand and measure the temperature of the planet when it moves just behind its star, as we see here. And another method is when we do things well, we can mask the star, collect the photons directly from the planet, and then we can do spectroscopy or imaging or coronagraphy. So what's exciting is that we're going to be moving on to this next stage very soon. And I will begin simply in a few years with Earth, a new generation of telescopes of very large size, 30 or 40 meters. And here I put of course, it's a mock photo, and this will allow us to separate among the numerous stars, the stars around the planet, and therefore to analyze the planet. And therefore, a very close future, much closer future, which is very exciting. You're all familiar with this. It's this new space telescope, 6.5 meters in diameter. You can see the scale, and you can see the people in the test chamber below. And I could not resist, for astronauts, you've already seen this, of showing you an extract of the deployment sequence of the Lagrange 2 telescope that will first of all been folded up and carried by Ariane. It's a NASA and ESA project. And of course, and this is very complicated. It will be 1,500,000 kilometers from the Earth with Lagrange, and we need to deploy the shield, which is the size of a tennis court. And then progressively, mechanically, the different parts of the mirror will look like a spatial telescope with incredible precision. It's your case, and it's the car for us as robots. When we look at this, it is absolutely terrifying. It's fascinating and terrifying at once. So we're all very worried. We will be trembling in 2019 when this engine is launched. And up until the end, until the implementation, which we will see in a few seconds here, of the secondary mirror, we will then at last be able to begin observing, and all of the astrophysicists involved in the project will take a deep breath and exhale. So, and that's with James Webb. So in a few months, we'll see, we're going to try and see things. But recently, we've made some two very interesting discoveries that are absolutely tremendous targets for the future major space telescopes such as James Webb and others. The first was the Proxima b planet, discovered a little over a year ago, that was named after the name of the mission. Oh no, it's the other way around, sorry. And so this is a small planet. It's a planet that's a little bigger than the Earth, very well positioned, that has good chances, if it's water-rich, to have liquid water at its surface, and that is only at 4 light years. It's the closest planet that we can have to the Sun, the closest exoplanet. Unfortunately, we can't see it from the side, but it could, for example, with a telescope, we could really obtain its characteristics. And one even better, a system that we call TRAPPIST, which was discovered by a Belgian team. And this is 7 planets of small sizes around a small star, not too blinding, not too bright. And therefore, we have a system of having a layer system. And this will be if we find an 8th planet, it's a little bit like The Little Prince or a literature competition, whatever we can do with this. It will be a tremendous celebration. 7 new atmospheres that we'll be able to analyze. It will take time. It will be difficult. Even with the James Webb, it's something that is ambitious. We have to share the James Webb with the cosmologists, etc. But we have some wonderful targets there, and I wanted to talk to you about them. As we're in an astronauts congress, when I was told to talk about exoplanets, I said, well, Mars, okay, that's the near future. No use of saying that we won't be going there soon to these exoplanets. You all know that if we take most rapid means of travel, it's Proxima 1, we will take 70,000 years to reach Proxima 1. So Thomas said that the astronauts are ready to do everything, but it's not easy. And of course, we won't be going there soon, but there might be some roles to consider. The first role, of course, is for astronauts, is inspired by Hubble. The idea that we can repair or improve spatial telescopes. For a long time, with the space telescopes, there was this tremendously complicated deployment system, and we thought about having a docking ring in order for Orion. So this was in Lagrange 2 at 1,600,000 kilometers to do something if there's a problem with deployment. So it would be terrible to have the secondary mirror that is stuck halfway. I think we really want to go there then. So I was talking just before with John Konefeld, who's here, and who I think he's on the photo actually in this picture, who did the 3 repairs. Oh, the servicing, sorry, the 3 improvements of the Hubble Space Telescope, and then was in charge of the project of the Science Directorate in the NASA. And he said to me, it would be very difficult if there was a problem, but it's always a source of inspiration. And above all, why not? Everything to do with man in space is so costly with regard to the exploration by robots and even space telescopes. But it was somewhat irrational. But we might say that among the projects that are in the boxes to make tremendous space telescopes, interferometers that are able to characterize an Earth at distance in a very precise manner. So in this project, we imagine mirrors that are structured with beams, and it was shown that men knew how to mount this within the scope of the International Space Station. So I finished. My conclusion is that we have experienced an extraordinary revolution. We proved, and this was not sure, that all stars are surrounded by exoplanets. Up and coming is to answer the question from the point of the environment. Because there are liquid oceans, does that mean that Earth is exceptional? And from that point of view, we don't need to find another Earth. We can observe any atmosphere, even very hot, even very cold. That will teach us a lot. It will answer a lot of questions. And then a question that I've barely broached, but maybe we can talk more in the question and answers. Will we then be able, thanks to these increasingly performant spatial telescopes, maybe one day detect a biosignature and identify life out in space?
Merci beaucoup. Tu nous rejoins? On va demander à Bertrand de nous rejoindre aussi.
We're going to ask Bertrand to come back up, please, so that we can talk together. I have a first question whilst Bertrand's coming up. First question for Sylvestre. Mars or Phobos, it's more easier. What's the interest of going to Phobos and what's the difference with Mars? Yes, I didn't talk about Phobos. I forget it sometimes. For everybody, Phobos and Deimos are two moons around Mars, one within the geostationary orbit, well, Mars at geostationary Mars, and the other outside. And Phobos, indeed, is maybe the simplest way of going to Mars. Phobos, we're not sure about its history. Is it an object that was captured by Mars? Is it an object that escaped from Mars following an impact? We have different theories, and in order to solve all of these questions, our Japanese friends from the JAXA have a very wonderful mission that will soon be, we'll leave them a short time to build it, but in the 2020s or so, 2023, maybe 2024, we'll be going to Phobos to take a sample and bring it back. And that is the simplest immediate access. As to whether it might be a good base for astronauts, why not? It is easy to capture, well, there's very little gravitational potential, so you know what's difficult for a body is to land, but then also to take off again. So with Phobos, it will be a lot simpler. Bertrand, you have any comments with regard to what was presented?
Je me dis que entre nous, on y croit tous.
Well, we all believe it. That exploration should have no boundaries. Now, this brings me back to another notion, which is also that of mankind, and that is the fear of risk. At the time of Apollo, it was exploration, and it was an international race, and the prestige of the country depended on this. Therefore, the risks that were taken were tremendous, but accepted. And we considered that one mission out of 10 would no doubt fail. And Richard Nixon had prepared two speeches at the time of Apollo 11, one for the success and one for failure. The one for failure was a beautiful speech, which was revealed 25 years later. The question I have now is our degree of bureaucracy, administration and risk aversion, will it make it possible to go back to the moon and to consider sending men to Mars? Because maybe that's where the limit is. It's not the explorer that is the limit, it's the anti-explorer that sets the limits.
Ouais. Je crois qu'on peut l'applaudir.
Yes, I think we can give him a round of applause. Listen, I would like to respond to that because it's quite true. You know, we say that to go to Mars there are a lot of technical problems to solve. There are some, of course, but we're talking about radiation, and this will be a problem. But it's a problem because we've established limits that are very low. No increase of more than 3% of chance of having cancer or other. If we go up to 5 or 10%, then I think everybody will still sign up for the mission, and all of a sudden it becomes magically a little more possible from a technical point of view. So I think in the corps of the astronauts corps, we're ready to accept the risk. But as you say, it's a question for society. It's difficult to lose a mission, above all, to fail in a mission, especially a visible mission. It would create problems. So we also have to approach that problem, because if you put a price somewhere, if the price is too great for human life, unfortunately, we prevent ourselves from achieving a lot in space, so we'll have to think about that. Just to add to that, of course, for manned flights, it's essential and it's very difficult to move ahead on this subject because we're not in societies today that are ready to take a big risk with regard to loss of human life. But this is a subject that space agencies are working on in the process of information because even regarding robotics, we have very significant costs. We built a culture that refuses failures. So when we set off on a mission, everything is done so that we are 100% successful. And in so doing, we have methods to develop our projects that cut all of the branches. With regard to the fireworks that you presented earlier on, that cut all of the branches off that because they're too risky. So we don't explore those branches. So the problem for innovation. So we're currently rethinking our design methods for our programs so that we can explore these innovative branches that are there in the heads of our engineers, but that we hurry to cut off because they're too risky. And so we have to work on this because it's a very big obstacle today, and we need to work on it.
The other question I would ask is, do we dare take the same risk as Saint-Exupéry, who discussed emotions and spirituality? Can we do it when exploring cosmos today? Who will dare ask the question, how was it created, and did someone create all this cosmos? Because the further we go in scientific exploration, the most mysterious it becomes without a spiritual explanation. And what spiritual explanation could we add to these scientific certitudes? It's a very good question. The first thing, François and myself have witnessed that you just wonder when you look at the universe around us. And the further you go, the more beautiful it seems. François worked on Pluton, and it's magical to a point that we could believe that nature has more imagination than we have. Curie, the comet that Rosetta went on for 10 years, 15 years, we had comet models which looked a bit like rough potatoes. And there you had these two comets with two rings around them. And once again, nature has more imagination than we have. Nature is beautiful. There's this aesthetical dimension. And we thank the agencies for this rule they've had, that all these images from space have copyrights, but are free from rights. So that means that some magazines can print them, you can discuss them in the media, and images go around the world without any copyright. So, this beauty just marvels everyone. Spirituality, well, everyone could have his own idea. For us, looking for traces of life in other places, you have to leave the spiritual aspect aside. And we consider life as carbon chemistry with some highly simplified elements like amminated acids. You've got to be extremely humble. Humility is key. We are extremely humble when we look at traces of life in the solar system, and you have to uncouple from this if you want results. Just one question for you, François. You discussed Plateau. This is the next European mission on exoplanets. What will this mission bring in continuation to what we have done previously? What can we expect from a mission like Plateau? And well, what will be the next breaking technology? Plateau, well, half our knowledge comes from a first mission we called Kepler. It was a telescope that scrutinized 150,000 stars, a very small angle. And sometimes a planet was coming in front, but it was a very, very small angle. I talked about Cheops test, and then Plateau came in with the same principle. And it's got 5-6 telescopes. You could have a great field of vision. It's 2,000 square degrees. For the sky, it would be 40,000 square degrees. We'll do it for 2 years. And we'll see planets that have orbits lasting even 2 years. Then we'll go beyond 6 years, 7 years, 8 years, and we'll make quite a remarkable inventory of what we have there. This was Plateau. You have looked at the stars. You haven't looked at all these stars, and we could do many missions like that. Something I haven't mentioned. We say European Space Agency, but in the pipeline, amongst the missions that have been pre-selected, you have some plasma missions, and there is Ariel, a space telescope. It might never fly, it might not be selected. We'll have the answer in a few years or few weeks. It might be the next breakaway technology, spectroscopy of the atmosphere, but this is for the near future. 20 years ago, we didn't know whether Earth was exceptional. There were theories like that. The distance of the planet from the Sun could be the contact between a star and another star. If it was the case, there wouldn't be that many planets. We know that it's universal now. But wait. If we have an ocean for 4 billion years, if this means life can start, you need plate tectonics, you need all these parameters. That might be exceptional. The Earth as an ocean planet, is it exceptional? I think we'll have the answer in the coming years, thanks to this breakaway technology, spectroscopy, and there will always be another answer. If you can have an ocean in other places, like Mars 4 billion years ago, did life appear? For life to start, life as we imagine it, you need incredible luck. So the acids will combine to make proteins and so on. It's inevitable, maybe. As soon as you have water, it works, but we don't have any idea. We do not know what is the transition between the non-living and the living. And we'll continue our inquiries on Mars. Mars had oceans. If it started even a little bit, we'll know. And we'll also look into Europa, see whether some shrimps or other living things. And we can do this in the near future too. And if it did start in the black, in the obscurity, it means it can be everywhere. And we don't know yet whether Earth is exceptional. There are 2 in the galaxies, or maybe there's hundreds of billions. It's a huge question, but in the coming years, we can probably answer it. Is it exceptional or not? Shrimps in geysers in slab, it's great. I think we could spend the whole afternoon discussing this. I thank you very much for this roundtable, and we will switch to the next one.
Alors avant la pause, je voudrais donner l'opportunité à Yannick Monger de s'exprimer devant vous. Yannick est romancier, auteur, prospectiviste et fondateur du comité Symbiome, dont il va nous dire quelques mots.
Bonjour à tous.
So, good afternoon, everybody. My speech will be very short. They asked me to be here with you for 2 reasons. As the founder of the Symbiome Committee, with lots of internationally known personalities, they are involved in the protection of the environment and peace. So, quite a number of friends like Bertrand, Jean-François Clairvoy, Jacques Rougerie.
C'est un organisme totalement à but non lucratif,
It's a non-profit organization, it's non-political, and we try to help a few projects. Amongst these, one very interesting major project, the Universal Declaration of the Rights of Humanity.
Et qui finalement sera débattu aux Nations Unies.
It will be debated at the United Nations. It will include the Declaration of Human Rights and the concept of collective responsibility humanity has to the future populations. So my goal this week will not only to try and convince you to support the Symbiom Committee, but also tell you about this project and try to make you ambassadors. I was also asked whether I could come with a few elements. I'm an author, I write novels, and I worked a lot in perspectives. And one of my activities is to try and simulate what the Earth could look like in the future using the technologies you know in the cinema, the pictures industry. So I'll quickly show you an image. This was done using one of Thomas' photos of the south of France. So there is so Thomas, if he's lucky enough to fly again when he's a lot older, like John Glenn, what he will observe of the planet will probably be very different to what he saw during Proxima. This is water going up. It makes for very nice pictures, but it's also very useful if you simulate phenomena like rising waters. It's interesting to protect the urban areas, trying to assess what can happen. It could be extreme phenomena like Irma, and this led to major inundations all the way to Houston. We were discussing that with NASA people yesterday. So it's a quick, typical simulation of what we can do. So.
Non, je crois que c'est pas échappe, c'est à la suite, Philippe.
They are looking for the right slide.
Sur lecture. Voilà. Et je vais terminer avec une petite animation.
So I'll finish with a quick video, as a picture is worth 1,000 words. So I'll show you a few pictures on music with a few citations. Some have been taken from the ground, some have been taken from space, a lot higher. And to finish, just to finish this session with music and to tickle your imagination. Thank you, Yannick.
La sortie son. La sortie son.
La sortie son, on était là normalement. Bon, on va le remettre après. Oui, mais bon, on remettra ça tout à l'heure peut-être pour vous la présenter en début de deuxième partie, puisque je vous propose maintenant.
At the beginning of the second session, I suggest we take a break now. We have 30 minutes break, and we meet again at 4:35 for a second roundtable related to space and Earth. Thank you.
va essayer de tenir le temps. Donc on va peut-être commencer cette deuxième session. Donc, Yannick Bonger, vous avez revu le film
Yannick Bonger, you have seen this little film again. Yannick will be amongst us all week, so if you want to talk to him, ask him about his projects, do not hesitate. He will be in the Congress with us all week. The second roundtable will deal with space for Earth and Earth observation as a strategic field, since man has been sending satellites into space. It's strategic for defense and observation. It's strategic, but the scientists immediately understood the benefits of satellites to observe the Earth, because humanity tried to understand how our planet works since man exists, and it's very difficult to study and think of something without having a distant view. And this is exactly what the satellites do. The scientists can observe the Earth as a whole, and it totally changes the observation context. Today, more and more parameters are being measured from space, and today satellites are measuring loads of parameters on the Earth, but also in the atmosphere, and that helps to understand how the Earth functions. We are becoming more and more aware, also thanks to the space industry, that it's key to maintain the spaceship of humanity, I mean the Earth. So to discuss our planet, the Earth, we'll do as we did for the previous session. They will come with us and we'll have a discussion at the end of the roundtable. Gilles Boeuf, professor at Pierre and Marie Curie University, president of the Scientific Council for Biodiversity, and Gilles Boeuf will tell us about biodiversity on our lovely planet. Good afternoon, everyone, and thank you very much. It's a great honor and a great pleasure for me to address such quality attendance. I'm used to conferences, but not always of this quality. I'm a biologue, and I'll tell you what this living matter can be. I took a few ecosystems. The Caledonian Recif. You have 5,000 to 6,000 different species per square kilometer. The coral reef is holding about a third of the species known in the ocean. The Guyana tropical forest in Amazonia, there's roughly 50,000 species per square kilometer in the forest. It's the richest ecosystem in terms of species. The Congo Basin and the two great islands, Borneo and New Guinea, Papuasia, hold more than half the species known on Earth. And what became of humanity? Shanghai, about half the population of France in one unique city. And humanity is going in this direction. I have to offer you two lovely pictures taken from space. The one taken from Apollo 8 in '68. It showed us the extraordinary beauty that all the cosmonauts have described. And it also shows its fragility. Bertrand Piccard and our physician friend told us how surprised they were when they were observing that, how marveled. But we have to be extra careful, otherwise, in a while, this will not be available anymore. It all started with images of supernova explosions, and there is a stone here from the Paris Museum. It's ugly. But what is the the role of a scientist. It's to tell a story from that stone. It fell in May 1864 here near Toulouse in Gers. This night, Toulouse was totally lit up by a rain of stars. It went to the museum collection. We studied it with nanoprobes. It was dated with chrome isotopes. They are 4.56 billion years old. It's about the time of the beginning of the Earth and Sun relationship. It went in space for so long. It fell, we picked it up, we forgot it, and now we're studying it. And this brings us back to the ocean. We shouldn't say oceans, there's only one on Earth. For 100 million years, the ocean has not changed. It is, if we had more than one ocean, our climate system would not work. Salinity, connectivity, and stability, that's the ocean. This dates for a bit more than 4 billion years. The Earth formed. Water came from the impact of billions of chondrites, each of them bringing the water particles. It formed this ocean, and 700 million years later, life started to develop. And here you have a composition of something that's quite interesting. It's your blood now. Why should we find the major ocean components in the ocean and in blood? Chlorides, 560 in the ocean. Potassium. Your blood tells the story of life on Earth, and it also tells the story of the emergence of the ocean. Life went out of the ocean and went to the continents, thanks to the estuary waters, mangroves, and thanks to salinity, these media that are still with us on the water side. And this is the oldest stone, cyanobacteria from Australia, dated 3.45 billion years. They invented this key relationship of the photosynthesis between light, CO2. It's a poison today, but it's extremely useful. All living cells in water are made of liquid. Water is the essential molecule of life, and with this we produce oxygen and sugars. This is how it all started. I could have picked that up 2 hours ago when we had lunch. In the water poodle, you have cyanobacteria in the water poodles here. They are 4.5 billion years older, but their composition is the same. I took some images from the major observatories, Paranal 4,500 meters, 4 infrared scopes. This is ALMA, 5,300 meters high, 66 antennas listening to the universe. Here you have the most powerful technology on Earth. You use it quite a lot here. And every day, what goes up to Paramal is a truck with agua potable, is drinkable water. And the best brains, the best physicians' brains need water. A human baby is made of 75% water. So water is essential, and the human body is at least as many bacteria on him and in him as human cells. The human being is an ode to biodiversity. You cannot do without it. And this life on Earth appeared on a previous mineral world. There is sodium, potassium, and our chloride. So what is this? It could be the Great Orion nebulosity you used to seeing explosions of novas and supernovas. But it's my world. This is one drop of seawater. We have 35,000 sampling sites. We bring these back and we sequence them. This is the truth of life on Earth since water has started in the oceans. You have produced is acquired, use hundreds of thousands per drop of seawater. I included a few million bacteria and some billion viruses. And when you swim on the seaside, you swallow them. But you're still just as beautiful, you're perfectly healthy. And this is the magical relationship between human and biodiversity. Your bed every morning contains between 1 and 2 million acarians because you slept in it. The human is totally emerged in biodiversity. All the grounds, 2.5 tons of bacteria per hectare, 3.5 tons of fungus per hectare, tardigrades, extremely resistant nematodes, acarians, columboles. This is life on Earth. 300,000 species known in the ocean, for 2 million known and described on Earth. On the soil, you have 26 times more species known in the soils than in the ocean. And we're destroying these soils. The collective agriculture we have today destroyed half of that. What are we going to eat tomorrow? Last ecosystem, what is this? This is digestive system of a human baby at birth. We've all been like that. And when a human baby comes into contact with the biodiversity, it's when the water patch breaks, the bacteria from outside his mum will contaminate the baby. And the baby will need 2 years to stabilize his flora. Autism, Alzheimer, type 2 diabetes, obesity are related to these intestinal bacteria. I come back to my plankton. Look at these fabulous pictures. You can marvel at physics, but us biologists can marvel at diatomia, dinoflagellus from the ocean. It's extraordinarily beautiful in every drop of water. And it's been like that for more than 3 billion years. Here in red, blue, grey, you have the gene sequencing we did in the ocean. In red, it's human baby only. In blue, only water cells. And in the middle, in grey, common genes. A third of our genes are common with the cell of phytoplankton. To show you the unicity of the living world, the human being came out of a system and is fully dependent of it. If he wants to leave the system, it won't do. So we have to stick to the history of the planet Earth. It's relating to technology. How did the human being stop being Homo sapiens? Ladies started making lots of babies, and we started having an impact on our environment. And we invented something really bad. And at the bottom of my slide, this is a stone. For more than 1 million years, it is the only tool the humans had. If you have to kill a boar today with one of these, the boar has a good chance of winning it. When I see kids in Congo using Kalashnikov, killing rhinoceros and elephants, it just makes you sick. This is what technology also brought us. Our rocket engines, our planes, our fax signs. Lots of you are pilots. Airplanes have been flying for 150 years, birds for 150 million years. Without the birds, we would never have invented planes. Then antibiotics, computers. And here you have the curve of demography, 2.5 billion humans on the Earth in 45. We're nearly 7.5 billion today. So things you are testing in space, like agricultural collectivism, we can cure that. Drinkable water, it can work. Deforestation, industrial fishing, this can be cured as well. Biodiversity going away, and pollution. Pollution is the disease of the 3 past centuries. What we cannot change, we can try to slow down. This is climate change. It has started. We cannot stop it, but we can stop emitting all this CO2. We can start removing the CO2 we've been injecting into the system for centuries. So the question now is biodiversity is in danger. We destroy, we pollute, we overwork the source. And climate change and human plays a role in there. We make problems worse. So space exploration is key to try and separate what's water and what is soil. We worked a lot on the rising of the sea level. It's 6.56 centimeters in the past 20 years. We have some very efficient satellites that did help a lot. The acidification of the ocean. We retrieve the CO2. We make carbonic acid. And if we do nothing, this is how it will end. And I'm very serious. All these lovely stories we're hearing there, I really admire what you're doing, what technology makes possible. And we can only do it in peace, not at war, not in chaos. And this is why biodiversity and ecology are key. We cannot escape that. We have to start working on it courageously, and we can make it. And it's the last picture. People attending the COP in Paris. We've seen Ban Ki-moon on an image with Laurent Fabius announcing the success of the Paris conference. 22nd of April 2016, the resolution in New York, we validated the Paris Agreement. We succeeded in doing that in November 2016, and we logged with ISS. The 2nd of December 2016, it's an American gentleman and a Russian. What did they say? We see our Earth, we love it, we admire it. And what do we see? We see pollution on the Mexican Gulf, pollution over China, Arctic becoming a desert, and forests burning. So hurry up, and thank you very much.
Merci beaucoup, Gilles. On peut parler climat et changement climatique, et c'est le sujet suivant. Pascal Lecomte est à l'ESA. Il est chef du bureau climat à l'Agence spatiale européenne.
He's head of the climate office, and he will tell you all about climate change.
Alors c'est très difficile de parler après.
Well, it's very tricky to speak after Bertrand Piccard earlier on.
Maintenant,
and now my colleague, Mr. Boeuf, talk about the climate. It's all been said. And I'm rather worried now. So my first picture is this one, and it was already presented. But I chose this picture because this is related to a discussion that I had with Jean-Claude Clairvaux during the climate conference, the COP21. You taught us this was the rising Earth on the moon on the 24th of June in 1968. It's the Apollo team that took this picture, and we discovered the Earth isolated in the vastness of space. We discovered its beauty, but we also discovered its fragility. So this world, which is very isolated, and it's thanks to you, the astronauts, that we discovered Earth. This morning, somebody was saying, you showed us the stars. It's true. But here you showed us the Earth. And I think that if we're talking about the climate today, it's thanks to you. The Earth is our space vessel. That's something that was already said earlier on. And you know, up there, when you're on board your spaceship, your life is hanging on by a thread. It depends on the proper operation of your spaceship. And for that, you have survival systems that you need to check. And to check the status, you have a dashboard which presents the status of all of the systems and subsystems. If all is green, all is well. Red, there's a problem. There are dials that show the pressure, the temperature, etc. Well, we did the same thing. As climatologists, we have the same thing. We have our dashboard. And our dashboard is the Global Climate Observation System, CHICOS. It is an entity that was charged by the United Nations to define which were the climate variables that had to be monitored and looked at closely in order to understand how our climate was changing. So from this list of essential climate variables, there are 55 variables, and out of these 55 variables, a little more than half are visible from space, and we need data from space in order to observe them and check them. In the ESA, we started a program a few years ago called the Climate Change Initiative, which consists in recreating from all of the space data collected since the existence of satellites, so for the beginning of the observation of Earth, in order to create time series. And one of the time series was showed earlier on the sea levels, so that they could be as precise as possible. The CCI, the Climate Change Initiative, represents 100 research organizations in Europe, a contribution to the 5th report of the GIEC, and therefore was used for the Paris Agreement. 350 articles and a review committee for high-quality scientific articles, and all of this is used to understand how the climate is changing. So I've taken a few examples, because obviously I only have 10 minutes, and it's very short. The climate of the Earth is changing. That is obvious. Denying it is stupid. It's denying something that is absolutely obvious. We are experiencing a changing climate. We have more elements of greater intensity, more heat waves, so heavy rains, heat waves, meteorological phenomena which are changing, an increase of average temperatures, 2 degrees in the past 50 years. This changing climate has an impact on life, on man, and on nature. There are more floods. A few years ago, the number of deaths caused by heat waves in France, forest fires, as we're seeing in California at the moment, droughts. All of this is related to the climate change. They're phenomena that are amplified by climate change. So rising sea levels, that was the curve that was presented earlier on. I think that mine is a little more recent. So the evolution from 93 to 2017 is 3.3 millimeters per year on average. But this can speed up. This can have sped up in recent years. Of course, there are ups and downs. There are times when the curve goes downwards. We can perfectly explain the phenomena that took place in 2012. We understand what happened. It was an increase in the water cycle. There was phenomenon of the La Niña that El Nino, which cooled the seas, and there was an intensification of the water cycle, an increase in the amount of rain on the continent, and all of this water in the continent was no longer in the sea, and it took 1 year, 1.5 years for this water to run off back into the sea. And so this explains the dip where you see the blue arrow. We understand these things, but on average we can see that the sea levels are rising by 3.3 millimeters per year. And what we discovered recently, but it's really only recently, until then we'd said, well, yes, the sea levels are rising, okay, it's the same everywhere, but not at all. There are places where it's rising faster in the red areas and areas where it's declining, the blue areas. So, for example, it's declining at the level of the Gulf Stream. What does that mean? It means that the current is changing. There's a new distribution of the water which is taking place. So the circulation is changing. The ocean circulation is changing. It also has an effect on acidity. So we mentioned the acidity of the sea. We measure salinity. That's one of the variables that we'll be starting as from next year within the scope of the Climate Change Initiative, the CCI. So we're going to be measuring salinity to try to better understand these phenomena. But climate change is not just the rising sea levels, rising slowly 3 millimeters per year. You say, oh, 3 millimeters per year is not a lot. But no, it's far more serious than that. We can see that it reaches 20 millimeters per year in some places. And as by chance, it's the islands of the Pacific Oceans that are 3 meters altitude above water. It will have a tremendous impact, and it will have a tremendous impact on populations. And the variables that we're measuring in this way are coherent, so we can understand what's happening. Here, the green line is thermal expansion, so the sea is getting warmer, and as any body that warms, there is an expansion. The blue curve is the increase in mass. The thermal expansion does not create mass. The blue curve is the expansion of mass, meaning that it is additional water that is feeding into the ocean. And this water comes from the glaciers that are melting in the Arctic. And when we add up both, it is the red line. And we find the line that we're measuring with gravimeters. And so we can see the amount of water in the seas. And this is coherent. So we can link the temperature of the sea, which is increasing, the waters that are melting from glaciers and icebergs, and this corresponds to the rising sea levels. And I wanted to show you these pictures of the Katia, Irma, and Josie cyclones last month. Sorry, 3 cyclones in the Atlantic. You see, that's exceptional. We've never seen that. No, not at all, actually. This is Carl, Igor, and Julia on the 7th of September 2010, and yet there is a big difference. Carl, Igor, and Julia were 3 cyclones of categories 3 and 4. Katia, Irma, and Josie are 3 cyclones of categories 4 and 5. Irma is the most powerful cyclone ever measured, and this corresponds perfectly to what we understand as climatologists about climate change. We've always said the number of cyclones will not increase, but their intensity will increase. And their intensity will increase because the temperature of the seas will rise, the humidity above the seas will rise, and this is the driving force of cyclones. It is the real fuel for the cyclone is humidity and water temperature. And this is exactly what we're seeing today. So we're 7 years down the line, and unfortunately, I would say, our predictions have come true. This is exactly what we were expecting. I wanted to close on the forest fires in California. Yes, this is also linked. Well, it can also be linked to climate change. We have an increase in drought. lower rainfall above California, and therefore we will tend to have more forest fires. We can see this, and once again, this is something that we predicted. We predicted the same thing in Australia, and there were terrible forest fires in Australia a few years back. So I just wanted to present these few pictures in some 10 or so minutes. That's it. Thank you very much.
Merci beaucoup, Pascal. Merci. Merci pour ces deux très beaux exposés scientifiques. Alors, les astronautes dans tout ça, est-ce qu'ils ont un rôle à jouer? Est-ce qu'ils se rendent compte de ces changements? Quel rôle ils peuvent jouer par rapport à tout ça? On va faire revenir sur scène Thomas Pesquet pour nous parler de son expérience à lui.
Thomas.
Alors, rebonjour à tous.
So, hello once again, everybody. Well, I am not a climate specialist, not at all. At the end of the day, I don't have much knowledge in that field, and I might as well say this immediately. The research that we do on the ISS is very little focused on the climate. We do a lot of medicine, technology, biology, but very few experiments directly to understand the climate. So why have I been asked to talk to you today? I think that it's linked to the fact that when all of my colleagues were coming back from space, I used to talk with them, and they all had the same discourse when they came back. They were all talking about the fragility of Earth. They were all talking about the beauty of this spectacle, but that we really had to protect it. I didn't really understand why, because you don't need to go to space to understand that. You can understand it in 20 minutes if you listen carefully. All of the data is available on the web. It's easy to access, and intellectually it's easy to understand. And yet, going into space changes things. What does it change? It makes us take a step back with regard to the Earth. There are very few jobs that allow you to extract yourself from the living world, to take a step back and look at the planet from above, and to really physically measure with your senses the global phenomena at the scale of the planet. Man is not made to do this. We're not made to understand phenomena that exceed us in scale and intensity. We're not made to understand figures with lots of zeros, at least not me. But to take this step back, to observe the planet from the low orbit over time. It's not the first day that I arrived in the space station. I can't put a date to it. But as I was talking with my colleagues, I realized that at one point, at a given moment, and maybe progressively, we shift towards an environmental, ecological awareness that is far stronger thanks to this view of the Earth from space. So I'm going to try and allow you to experience this within this room. Many people have experienced this before me and could no doubt speak more eloquently about it, but I've been asked to do it. So I'm going to show you with a few photos just how far from a beginning of an observation mission we can move from the beauty of the Earth to the observation of, unfortunately, of its fragility and the harmful effects of human activity. So this is a very nice photo. I'm not saying it because I took it, but artistically there is contrast, there are very structured square zones, there is color contrast, but this is in Arizona. What does it show? It shows that on one side we have irrigation, you can see the luxurious green, on the other side we don't, and it's the desert, with water drainage systems at the bottom of the photo. These dark lines are the water drainage to use the water in the left part of the photo around the city. So what might seem a quite harmless photo, what does it show us? That we have to be careful of water resources. And my photos are going ahead of me. It shows I'm not speaking fast enough. Well, it shows us that there can be problems of distribution of water throughout the Earth. So with an artistic, rather standard photo, it can eloquently talk about the climate. Here we have the Delta of Salon in Senegal, and this is a mangrove ecosystem. Once again, very beautiful, curved lines, a sort of harmony and a palette palette of pastel colors. But you can see on the bottom left of the photo, it's a very fragile ecosystem. And we said this, the coastal areas, the mangrove zones are the very first to be impacted by climate change. So once again, these photos speak to us. What do they speak of? The fragility of Earth. A very beautiful photo once again, beautiful colors. I was very happy to do this. It's the Betsy Booker River in the west of Madagascar. Until we realized, you see those red zones? It is the soil that has been laid bare. It's deforestation, it's drainage, it's erosion that has removed all of the sediments of the alluvions. And this is bare earth, and that's why it's so red. It's almost blood red. Once again, a beautiful photo which tells us about the mankind's destruction of the environment. A cold zone also. We're talking about glacier melt. This is the Alps. You can see this rather unctuous texture of the glaciers. It's very pretty to observe, but from the space station over a long period of time, of course, not in just one mission, not in 6 months, but mission after mission, on the astronauts' photos, we realize that the glaciers, the size of the glaciers, the glaciers are shrinking. And this makes us think we're talking about the increasing sea levels on the planet. This water comes from somewhere. It comes from ice melt. This is a more marine photo. I'm taking you across the planet once again to better show you what I saw for 6 months. This is the barrier reef. Wonderful from the space station, but in a few years it will probably be far less spectacular because you know as well as I do that it's being progressively destroyed. We're destroying these treasures of biodiversity, and we can capture this on our photos from the space station. Another nice photo. This one is quite funny because as a former pilot, I used to like photographing airports. And then as I was looking at this photo, I realized that this was in Jordan. And normally, we should have seen the Azra Oasis, which is a big, luxurious oasis in Jordan. Unfortunately, it no longer exists. Why? Because the aquifers and the groundwater have been overexploited. And we can see traces of water at the top left of the photo, but all of this is very dry. And once again, it is climate change at work that we can see in the astronauts' photos. New Caledonia. I'm happy that you talked about it earlier on, one of the spaces which holds the greatest biodiversity. And once again, in the Pacific Ocean, remember the map with the rising sea levels, right in the middle of the red zone, if I'm not mistaken, a zone which is really fully faced with climate change and rising sea levels. This is a nighttime photo because we also observe Earth at night. What does this mean? It means a lot of things. Well, first of all, that there are a lot of people on the Earth. We talk about light pollution, but above all, for me, it's above all soil utilization that we see. Europe, the west or east of the United States on a night photo is very beautiful. It's just a carpet of light, but this raises the question of, isn't there a little too much density in these areas? And you see above, this is something that is shocking each time. It's the fine layer of the atmosphere. Many of you have seen this before me and described it far better than I have. This fine layer of the atmosphere is the envelope that protects the Earth. It's what contains life on Earth. And from the space station, what does it look like? Just like a soap bubble. It's that fine. It is armoring against death, against the empty void of the cosmos, and it just looks like a soap bubble. When we realize that after weeks and months in the space, we see our planet somewhat differently when we come back to Earth. River pollution, we talked about the pollution of cities, atmospheric pollution. I would have liked to show you a photo of certain cities in China, but unfortunately I cannot, because there is such a constant layer of pollution, and in a 6-month mission you cannot photograph them. This is the mouth of the Rio de la Plata, 206 kilometers wide, that carries so much sediment, Argentina on the left, and you can see that it drains the land upstream. Is that normal? No, not really, because it means that land upstream, unfortunately, are not properly used. And once again, we're destroying this ecosystem as we go up into the Amazonian forest. This is a photo of a glacier, and here, this is the Viedma in Argentina. It's the greatest mass of ice in the southern hemisphere, 55,000 cubic meters of glacier. On the astronauts' photos, if I show you the same photo in 10 years' time, if I look at the photos of 10 years ago, we can see a clear evolution, and we can see just as well with a curve of dots going down. But here we practically feel it physically from the space station. We feel physically the need to protect the Earth and the distress of certain areas. We can see the trees cut in the Amazonian forest. Many of you have seen this before myself. I tried to photograph it to show it, but I'm really not the only one. Sometimes the forest is cut bare and it goes up along the river and it goes out from the riverbeds, and it shows the damage that we're doing to the Amazonian forest. The glaciers, this is once again Peritoneino in the South America, which a few years ago stretched far further into these areas, and today is withdrawing more and more inland into the mountains. Another picture of the same glacier. So all of this was to show you what is happening, the phenomenon of withdrawal, of understanding that we have above the ISS, because we spend a lot of time looking through the window. If we try to identify what we're seeing and not just look at the Earth going past like a beautiful show, this is to show how far the Earth is fragile. We saw photos of the blue Earth, of the rising Earth behind the moon. That's beautiful, but I would like to go further. I'm going to show you the pale blue dot. This is Voyager 1, more than 4 billion miles from Earth. The Earth is this little dot, this little blue dot, hence the expression. And this shows that we really are all alone in the universe. I would like to show you an even prettier version. This is Cassini, a very beautiful mission that has just finished, and which shows the Earth. You see here, the moon is quite visible too. As a little dot on the photo, we are very fragile. We mustn't make the mistake of thinking that we're strong and eternal, because what space tells us, what space observation tells us, what satellite tells us, but what astronauts coming back to Earth tell us, and they can come back and talk to us about it, as robotic probes cannot do, is that all of this is very fragile. And I kept Curiosity for the end, which, since Mars, all alone on that little planet, took a photo of Earth. And this really does place things in perspective. I don't know if I've managed to really allow you to feel this overview effect that is in the field of emotions and feelings rather than scientific analysis or technical analysis of data of the Earth. But what I'm certain of is that I agree with Bertrand Piccard when he says we hold a responsibility. I think that having this point of view is, we're very lucky. Not many people have been to space, and we have to raise the question of what we do with this. What do we do with all of this? Of course, we're carrying out our scientific and technical missions. That's what we're sent out to do. But do we not have a bigger role than that? Should we not become the ambassadors of these things? I think that the answer is yes. And to be lucky enough to go into space brings duties with it. And the duty that we have today is to talk about all of this, to talk about this view that we've had the chance of having from space, from our orbit, to talk about the fragility of the Earth and try to convince everybody that unfortunately today we have no B plan. Earth is our only space vessel, and if we want it to go far, then we have to take as good care of it as we can. Thank you very much.
Merci Thomas. Je peux demander à Bertrand justement de nous rejoindre.
Thank you, Tom. I'm going to ask Bertrand to join me. I have a question for Gilles on biodiversity. We know that temperatures are rising. Regarding biodiversity, we know that biodiversity is declining. We're sure about it. How do we apprehend this? Because there are new species that are created as well. How do we measure all of this? And what is the status of biodiversity as you described it? Well, it's more complicated than that. In fact, since life has existed on Earth, about 4 billion years, it's gone through episodes of ups and downs. But due to the cumulative aspect, despite the crisis, we think that we moved from a maximum of species about 2 centuries ago. And now we started to decrease the number of species that we have. So we know the vertebrates, we know the number of fish, the birds. What do we know about the animal life on the soil or the plankton in the ocean? With regard to life on Earth, I don't want to talk about extinction, except for the sturgeons that are disappearing in Gironde, the rhinoceri. If we continue as we are now, in 10 years' time, there will be no more. But having said this, there is a decline in the number of species and living species, and this can lead to an extinction. So the problem is that today we're creating the conditions for the disappearance of species because we're changing everything. And living beings like change, but not too fast or not too brutal. If there had been no climate change until today, we would have had a marine species and continental species, but it goes too fast. So regarding the condition of species, for example, we find mosquitoes now in the London Underground. 2 new species have appeared in the underground since the 1930s. They appear in the underground, it's hot, there are no other animals to eat them, and there are tons and tons of human blood to drink. So as the ecosystems change, they don't have the time to express themselves. So the results are very bad at this point. When we're talking about climate change, what is the share made by mankind and what is the natural share? Because it's quite obvious that there have been variations over history, far slower than today. So what is important are the arguments that we can have in order to manage to convince people. So I have curves that I could show you. I have a lot I could show you. I would like to just come back and explain one curve. It's the amount of CO2 in the atmosphere. We went back thanks to boreholes in the polar boreholes. We went back to 800 million years in the past. And what do we see? We see a nice oscillation of the curve and the quantity of CO2, and oscillates between 130 ppms, that's particles per million, to 300. And out of 800 million years, we can see this curve, 5 or 6 oscillations of this kind. And we slowly come up to 1750. And what happens then? It so happens in the 1715 we're at a peak of this curve. And there, it goes up all of a sudden peak. And last year, we went from 400 ppms. So it means that in 150 years, we've gone from... We doubled the amount of CO2 in the atmosphere. So we've gone from a curve that was gently oscillating between 130 and 300 ppms to more than 400 ppms. And it's not a scenario, we're not in a scenario where it will decline. Only mankind can have done this. It's quite simple. We can clearly see on the curve, it begins in 1750, and it begins with the steam machine, when we started burning, mining coal, and it exactly corresponds to that peak. And there's an exponential rise as from that time. And only mankind can have caused this. There is no other explanation possible. There is no other model possible. I entirely agree that there is no other explanation than mankind for CO2. But what I need are arguments to convince those who say to me that during the 800 million years, where there were peaks and dips, the sinusoid curves of CO2, that there were periods of glaciation that invaded Europe and then disappeared without a variation of CO2. And when I see people who say this, I need arguments to answer them. Well, it's more complicated than that. You can't just explain it in 5 minutes. But it's quite obvious that the climate system is a very, very complicated system. You cannot restrict things to CO2, to the sea temperatures, to one. We can't extract one single parameter. Even the argument that consists in saying, you see, there were floods last year, that's due to climate change. It's wrong. You can't say that. It's a statistic event. It's an event that occurred last year. It was exceptional, but there have been other exceptional events in the past, and there will be in the future. To link an exceptional event to a long-term phenomenon is not possible. It's statistically, we need to come back over the past 50 years and say, well, yes. But I think that the criterion which, one of the criteria, and I was looking at that last night, but I didn't find the curve which really illustrated it well, is the reassurance companies. If you go onto the website of Swiss Re or Munich Re, those people say, I am obliged to include climate change in my accounts, because if not, it won't work. So it's an economic phenomenon, so it's the reverse of what, that's what you were saying earlier on, meaning change helps, etc. But they were saying, if I want to survive, then I need to take into account the effects of climate change, the Katrinas, the Irmas, and all of those phenomena, droughts, forest fires in California, etc. For me, all of these are phenomena that are related to climate change, and I must take it into account. I just want to answer Bertrand on temperatures. There was an Australian article published in 2014 when they looked at the average temperature of the sea and air for the entire planet during the 20th century, month by month. And every passing month, we compared the average of the past month with the average of the 20th century. We need to go back to February 1985 to find lower temperatures. So that makes about 400 months, and no phenomenon without human intervention happens in that way, in an absolute direct way. So there is no month below out of 400 months, and the probability is 1 out of 200,000. So I'll let you conclude on the influence of mankind on temperatures. Thomas, a question for you, for the astronauts and their view of the Earth. You were lucky enough to do a long flight. The way in which you saw the planet, did that change during your flight time, and in which direction? And how did it happen over time? Yes, it's a good question, indeed. I think that the way we see the Earth changes for two reasons. Firstly, because we learn all about the planet during a space mission. After a while, I realized that even without wanting to, as I was looking through the window, I could see almost exactly where we were. Is it the middle of Australia? Was it the Sahara Desert? Was it South America? All of that at the beginning is not easy because there are things that look similar, and we're not experts in geography. But after a time, we learned the planet by heart, and in a single glance, we know where we are. So that's really good, because it means that we're starting to look at it with an expert eye and saying, well, now I know where I am, and we can look in detail. And when we look at the details, unfortunately, things that were only beautiful to begin with sometimes become very worrying. And once again, there might be some experiments to do. At what point does this change happen? Is it after 2 days, 3 days, 1 month, 2 months? I don't know. I'm happy to be here because we can no doubt talk about this with all of the people and try to define a timeline with this awareness. But it's quite obvious that our vision changes. We didn't talk about politics either. We're talking about the environment. But allow me a little aside here. Once again, if we take photographs of cities, I could never manage to do it. Why? Because when you look at a map on Earth, we have nice maps with borders, but within a continent from the space station, there is no difference. And sometimes I was 400, 500, 600 kilometers out because I didn't have that nice red line that separates the two countries. What does that mean? It means that these are constructions of the mind. There are many constructions of the mind in Earth, and increasingly seen from the space station, you can't see those boundaries. So beyond the ecological and environmental awareness, I think that there is also a small political effect that we take back to Earth with us. Thank you. Bertrand, a word of conclusion for this part? I think that everybody agrees with everything that has been said here. You could be in another conference where everybody else would also be in agreement. And that is to say that the industrial world has created jobs, has provided comfort, mobility. That it's obvious that there has been a very high environmental cost, but without this, we wouldn't have any satellites either. There wouldn't be any rockets, no planes, no pilots, and we would not be here today. And it is this incredible contrast between the two faces of mankind that we need to manage today. And in fact, I think that it's a conflict between the long term and the short term, because in the short term, we need to have companies who pay wages and who have a certain number of imperatives, and if they close today, the global economy will crash and mankind will go through a total humanitarian crisis. And then there's a long term where we'd have to take into account everything that will happen later. But it's not because the ice in the South South Pole will melt in 20 years' time, that people will not take their cars to come to work tomorrow. And the conciliation of both needs to be done in looking for solutions and not complaining about the problem, because when you're complaining about the problem, you can't move ahead. And the solutions today, I would like to recall, exist today at a sufficiently high level to divide CO2 emissions by 2, thanks to energy efficiency, which would save or which would reduce the tremendous waste of energy and raw materials that we have today. Our problem is in waste. It's not in our lifestyle. And this is where the political world should be represented here. We should here and now have politicians who take the commitment to fix within the environmental and energy goals of their policies the use of solutions that already exist today. And there would be tremendous change.
Merci Bertrand. On y travaille,
on y travaille. We're working on it. We're working on it.
Bon, on est à peu près dans les temps.
Right, we're pretty much on time. I would like to take home the phrase explore to make the world a better place, and space is my future because it is the motto of this Congress. So I would like to call up on stage our 2 speakers of the first roundtable, Sylvestre, François, to thank you all for these very interesting presentations. I hope that you spent a very good time with us this afternoon. Thank you very much to all of the speakers. We can give them a round of applause.
Merci à tous et je vous souhaite à tous un bon congrès et une bonne semaine.
A very good conference and a very good week together. And thank you to our moderators.
Merci. Merci beaucoup. On vous attend en salle sérieuse pour ceux qui peuvent là. On vous attend en salle sérieuse.